So next is cluster sampling. When we have a very large population, then cluster sampling is used. And what cluster sampling means, a cluster means group of elements. For example, in a survey, we may have houses in city as elements and city blocks will be clusters. So in this, we first select a random sample of clusters and then collect data from every, and this is important, from every element in the selected cluster. So sampling units here are clusters. So sampling units principle using for cluster sampling is what? The mainly it is convenience, and the other is the convenience, and the other one is the reduced cost. Why is it convenient? Because instead of, we may not have a whole list of all the houses in the city, but a map of city blocks, and we can use it. And then there is reduced cost also, because uh, when you have a large population spread around, and if you collected SRSWOR for 90 units, and 90 units, one is sitting here, one is here, and one is here, and one is here, while if you do clusters, you collect all data from this cluster and this cluster and this cluster, it would be much more cheaper to do that. So however, but for a given sample of elements, sampling of individual elements from the entire population usually gives a more precise result than sampling clusters. So sampling is convenient and but it is less precise than SRSWOR. So what we want really is that the clusters need to be as heterogeneous. Cluster it themselves need to be heterogeneous, and different clusters should be as similar to each other as possible. So cluster within cluster, there should be a lot more heterogeneity, while different clusters should be similar to each other. But how do we form clusters? Clusters, you can generally, we choose clusters based on naturally occurring clusters, like city blocks, departments in a firm. And how do you select the size? Obviously we want them to be bigger. We want their variance to be less, but uh, we also want to control the cost. So variance and cost are two competing factors. So we have a something called a cluster sampling, and there is another thing called as stratified sampling. What is the difference between these two? In cluster sampling, we select the clusters, say these are the clusters, we selected this and this, so we'll count every element in this and this, we will do nothing with this and this and this. Okay, Here in stratified sampling, the population is grouped into strata, and then within each strata we select a random sample of elements. Within each strata. So some elements are observed from each stratum. In this case, in cluster sampling, elements within a strata, in stratified sampling, we want the elements within a strata to be as homogeneous as possible. While so within strata, we want them to be homogeneous, while within cluster we want them to be heterogeneous, to be more precise. So now we have to do a couple of things. One is we're gonna go three things. We're gonna do estimation of mean in clusters of equal size. Then we're going to do estimation of proportion in cluster sampling with cluster of equal size, and lastly we will compare the cluster sampling with clusters of unequal size. So estimation of mean in cluster sampling of equal size. Okay, so population for example can be divided into n clusters, and each cluster is consisting of t elements. So obviously the total population will consist of nt elements. Let Yij denote the value of a target variable y for the jth element in the ith cluster, where I is equal to 1 to all the way to n because there are n clusters, and j is going to be 1 to all the way to t because there are t elements in each cluster. So what is going to be the y bar, which is the population mean? That is just going to be 1 by nt summation I to 1 to capital N, and summation j is equal to 1 to t Yij. And what will be the variance among the element, or S square, for population is going to be 1 minus 1 upon nt minus 1 summation I is equal to 1 to n, and then summation j is equal to 1 to t Yij minus y bar square. So that's the population values, right? What happens if we select we do cluster sampling, and a sample of n clusters by simple random sampling is selected from n clusters, and each element of them is observed to collect data. So sample consists of, now the sample will consist of nt elements. If Yij is the observed value of target variable y for the jth element in the selected clusters, here I is going to be 1 to small n, and j is going to be still the same, 1 all the way to t, then y bar is going to be 1 upon small nt now, and summation I is equal to 1 to n, and summation ij is equal to 1 to t Yij. Next thing is about a something called intra-cluster correlation. Intra-cluster correlation indicates how strongly the elements within a cluster resemble each other with respect to the variable y. How strongly the elements within a cluster resemble each other with respect to variable y. So rho is equal to 2 and that's the formula t minus 1 nt minus 1 s square summation I is equal to 1 to n summation when j is less than k. Now j and k are just two variables or two elements in a cluster. In this case we're gonna do y I j minus y bar and y I k minus y bar, and then so for each of the clusters, n clusters, we have one value of j and one value of k where j is less than k, and then we're going to calculate y for j element in the first cluster and subtract from y bar, and then the kth element in the same cluster and subtract from y bar, multiply them, and then keep adding it for all the clusters. So anyways, so that's what its rho is. Obviously we will see that which have the homogeneous within clusters, the rho is going to be more than 0. So if variability within the cluster is more than if variability within cluster is more than variability across clusters, then rho is going to be less than 0, and which is what we want. But in majority of the cases you would note that the clusters are generally homogeneous, so the rho is more than 1, and which is not something we want. So now we have seen the y bar, the big y bar and the small y bar, but what about the estimation of the population mean and its variance? So when a simple random sample of n clusters, each consisting of so we have n clusters, each consisted of t elements, is drawn from capital N clusters, then y bar is unbiased for capital Y bar, and the variance of y bar is variance of y bar is equal to 1 minus f upon n t minus 1 upon t square n minus 1 s square 1 plus t minus 1 rho, which can be simplified somewhat to 1 minus f n t s square 1 plus t minus 1 rho, where f is n upon n. Now instead of doing this cluster thing, if we had obtained a direct sample of also nt from SRSWOR, then we will find the variance of the sample mean. In that case is going to be 1 minus f nt s square, which is basically you can obtain this from the typical formula that we know, s square 1 minus n upon n. So we did this. So we can say that in variance, so this whole thing is the same. This whole thing is the same, but we get this little thing additional here. Actually, this thing is also there. The only thing that is added is 1 plus t minus 1 rho. And as you can also see that if the rho is positive, then this whole thing is going to be more than 1, in which case the variance of y bar by cluster sampling is going to be more than the variance by SRSWOR. So if rho is more than 0, then variance by cluster sampling is more than variance by SRSWOR. So if rho is more than 1, cluster sampling is less precise. In surveys, we pretty much always have a rho more than 1 for cluster sampling. So cluster sampling is generally less precise than SRSWOR. Okay. Next is estimation of proportion. So we have seen the calculation of proportion by SRSWOR previously. How do we do this? So element in a population can be classified into two classes, right? We're going to classify them into A and A complement. Our objective is to estimate the proportion of elements in the population which belong to the class A. So proportion of elements in A, say, is P, and AC is going to be Q, which is nothing but 1 minus P, and we want to estimate this P. And of course there are n clusters, and each cluster is containing T elements. Now AI is the number of elements in the ith cluster which belong to class A, where I is 1 to n. Proportion of elements belonging to class A in proportion of element belonging to class A pi, the small pi in this case is going to be AI divided by T. T is the number of elements in each. So in cluster sampling, we only doing selected clusters, so we do not know the we will know this proportion in all the clusters, right? So I is 1 all the way to small n. And the P is going to be 1 upon n. I is equal to 1 summation to n pi. and then this is basically, because pi is ai by t, this is just going to be nt summation I is equal to 1 to n ai, and this is the small p, which is an unbiased estimator of the population p. Now question always comes about variance. What is variance of the small p? That is going to be n minus n summation I is equal to 1 to n pi minus p square n minus 1, which can be simplified into n minus n square n summation I is equal to 1 to n pi minus p square. So this is the variance, and we are calculating pi's minus p. For large n we can simplify this. Now again, we had directly selected NT element from population of NT element using SRSWOR. Then variance of P using SRS is going to be NT minus NT upon NT minus 1 PQ over NT, which is very much n minus n upon n PQ over NT. And then we compare this with this, we can see that the variance of P using cluster sampling is equal to variance of P using SRS sampling multiplied by something, which is T I is from 1 to n pi minus p square upon n pq. So cluster sampling, this estimator has a multiplying factor. Now if the within cluster variability is less, then this number is going to be very small, and particularly if n is very large, then this is not a big difference. So in cluster sampling, the preference is going to be that this number is small, and there is not a too much difference between the clusters. But this is, but obviously the SRSWR would always be preferred. Now so far we have covered the cluster sampling with equal size, but in majority of the situations we actually don't have equal size, and we have unequal size of clusters. So estimation of cluster sampling with clusters of unequal size. In most situations, when cluster sampling is applied, cluster will consist of unequal number of elements. Suppose population can be divided into n clusters of unequal size, and let the ith cluster consist of ti elements, where I is equal to 1, 2 all the way to n. The population then consists of I is equal to 1 to n ti elements, right? This is the whole population, because each unit we're going to go from I to n, and each has a different number of elements, so this is the total population element. And let yij denote the value of the target variable y for the jth element in the ith cluster, where j goes from 1 to ti, and I is 1 to n. Then the population total of the ith cluster yi is going to be j is equal to 1 to ti yij, and the population mean is going to be a summation of I is equal to 1 to n yi's divided by I is equal to 1 to n ti's. So it's basically taking the form of a ratio between the two variables. Now of course we want to do is we want to estimate the y bar. Now we have selected n small clusters, and then we have the y1 and all the way to yn would be the observed total of the n selected clusters. The t bar is going to be 1 upon n summation I is equal to 1 to n ti. This is the average cluster size of the population. Then the estimator of y bar hat, which will be same as y bar, is going to be I is equal to 1 to n yi's divided by I is equal to 1 to n ti's, and its variance, the variance of the y bar will be given by 1 upon n minus n st square divided by n t bar square, where st is given by 1 upon n minus 1 summation I is equal to 1 to small n yi minus y bar ti. What is y bar ti? Y bar ti is just the whole basically y bar is sum of each, and then ti is the count in that, and that would give you the mean total. So this is the mean of all the y's, and then this is the ti. So and then you square it, that is the st. But obviously this requires a calculation of t, and t is unknown. Then we can replace it with the whole ti. If the t is unknown, then you can't do t, and then in that situation we can't get the capital T bar, because for capital T bar we need the whole n and whole population's number. So we can just do is, instead of 1 by n, we can use 1 by n I is equal to 1 to small n ti, and but this we would know because we are doing it for the actual element in the cluster, so we might know the ti for that. But both the yi as well as the variance of y bar will be biased. Bias will be small, and estimated variance would be good estimator of variance of y bar only if the n is large. Say n is more than 20, then only the bias would be less. So you have to have a larger sample size. Now I is equal to 1 n ti is equal to to denote the population size. Then t bar is also to divided by n. So population total y can be estimated as to y bar, and its variance can be calculated as to y bar is equal to to square variance of y bar which is nothing but n square 1 minus n upon n st square by n. Now if you think that this equation is A, we don't often know this information. In that situation, what we can do is y hat c is equal to 1 upon n yi. This is the average of cluster total for n selected clusters. We can calculate the population total y hat, or estimate it as n times yc bar. That is equal to n upon n summation I is equal to 1 to small I yi. So estimator of variance of y hat is just going to be n square 1 minus n upon n sc over n, where sc square is equal to 1 upon n minus 1, I is equal to 1 to n yi minus yc bar square. Now if cluster size vary greatly, then this equation is B. If the cluster size are very different, then the variance in the B is going to be variance in A, or variance of n y c is going to be variance of TO y bar. But if we don't know TO, then we have to go with this one. So if the size vary a lot, then NYC is not the right thing to do. We should be going with the TOY.